Okay, so we're going to go over the review for 3.3 to 3.6. Before we actually start on the review though, some things that would be helpful to make sure that we're all ready for the test is knowing the derivatives of our trig function. So this on the screen here says d over dx of sine x. What that's asking is what is the derivative of sine? And so we simply need to have these memorized. Simply, it may or may not seem that simple to you, but they're really not that bad. Most of us probably have memorized already without even much effort that the derivative of sine is cosine and the derivative of cosine is negative sine. And from there we can actually do a couple things. Remember, all of our trig functions that start with c's are negative. So cosecant is going to have a negative and cotangent is going to have a negative. From there, if you can memorize what tangent is, cotangent will be similar. If you can memorize what cosecant is, secant will be similar. Tangent and secant, believe it or not, actually go together based on trig identities. From last year in trigonometry, we had an identity that said 1 plus secant squared x equals tangent squared x or something like that. So that relationship between secant and tangent was established last year. So the derivative of tangent x is secant squared x. Okay, and that doesn't necessarily have to do with this this identity. It actually might if we tried to prove it. I don't know. But tangent is secant squared when I take the derivative of it. If I can remember that tangent is secant squared, cotangent is going to be negative cosecant squared, because just like tangent and secant go together, cotangent and cosecant go together with these identities. So if I can remember one of them, hopefully I can remember the other one. Cosecant and secant also have a similar thing happening. Secant is secant x tangent x. So secant has secant and also the trig function that ends up being associated with secant, which is tangent. So cosecant is going to be negative cosecant x cotangent x. So you need to work on memorizing those if you haven't already, and that's kind of a way to look at them as being connected. Instead of memorizing 6 things, it's really more like you're remembering 3-ish, kind of. The other thing that I want us to make sure we know before the test is the product rule and the quotient rule. We also need to be able to use the power rule and the chain rule. The chain rule is the most recent thing we talked about, but it's helpful. Like these are easier to write down. So the product rule, there's 2 ways of writing it down. There's the phrase that we can memorize, 1d2 plus 2d1, which means write down the first, take the derivative of the second, plus write down the second, take the derivative of the first. The other way of writing it down is where we say u v prime plus v u prime. If I were to ask you just randomly to write down the product rule, I would be okay with either of those answers, whichever one you want to write. The quotient rule has the same thing happening. That there's 2 different ways we can write it. One way is low d high minus high d low over the square of the one below. Something to that effect that gets that point across. And then in our u and v situation, that would be v u prime minus u v prime over v squared. And so if you're writing it this way, then you're starting off with u over v. So v is the bottom, u is the top. So low d high minus high d low over the square of the one below. So whichever way you want to have this memorized is fine, and depending on who you are, one of these will be easier to memorize than the other, and that's fine. Just if I were to ask you, I'm not saying I'm going to ask you, but if I were to ask you to write down these 2 rules, these are the kinds of things that I would expect to see. Now on to the review. We start off here just taking derivatives, and they're fairly simple derivatives. We ended up getting pretty complicated toward the end of this, so don't forget that some of these are actually pretty easy. These are just using the power rule. So I multiply by my power and then take one away from my power. So this is going to be 3 times 4, which is 12, x to the third, because 3 is 1 less than 4, plus, and then I do 3 times 8 and subtract a power to get 2. The derivative of just a number is going to be 0, so I don't need to write anything else. It asked me to find dy over dx, so I would put dy over dx equals, and that's my answer. On the second one, the only thing that makes this tricky is we've got fractions, and some of us don't really like fractions. So dy over dx equals 1/2 times 10 is 5, subtract a power. 3 times 1/3 is 1, so minus x squared. Now on these next couple, in parentheses, you'll see product rule. So that's me trying to give you a hint as to the way to do this. So in the product rule, we're either saying 1d2 plus 2d1, or you're using u's and v's, whichever way you want to do it is fine. But what I need to do here is write down the first thing without doing anything to it, and then take the derivative of the second part. So you're going to multiply by the power and then subtract 1. So 6x squared, multiply by the power, subtract 1. 1, the derivative is 0, so I don't need to write that. That's 1d2, or uv prime, plus, I'm going to write down the second one without doing anything to it, and then write out the derivative of this first part. The derivative of 5x minus 4 is 5. Now, the biggest mistake that I tend to see with this is either accidentally putting a minus sign between. In general, in math, multiplication and addition go together, division and subtraction go together. So when I'm doing the product rule, which is multiplication, I'm going to add between them. When I do the quotient rule, which is really division, I'm going to subtract between them. The other thing is that I want you to FOIL and distribute, and it is easy to mess that up. So just be really careful as you're going. 5x times 6x squared is 30x cubed. Then negative 10x squared. I'm FOILing right now, by the way. Minus 24x squared, and then plus 8x. Then I'm going to distribute the 5 here, and there's a plus in front, so none of these signs will change. This will be 10x cubed minus 5x squared plus 5. So I'm going to add some like terms here. There is 30x cubed and 10x cubed, which is 40x cubed. Then negative 10x squared, negative 24x squared, and negative 5x squared will give us negative 39x squared. And then I just have plus 8x and plus 5. All my like terms are added together, so this should be my answer. It's really easy to make mistakes on this, and so I just want to point out the only thing that we did that was calculus was this first step, and so you're going to get most of the points just for doing that step right. From there, if you make a mistake, then you would get a point or two off depending on how bad your mistake was. If you just mess up one of these things and then that throws off your answer, that's a point off because we need to be more careful as we're going along. But if there's something more serious wrong with you simplifying it, then maybe 2 points off instead of just 1. So keep that in mind as you're going. It's okay if you mess up. It's not the end of the world. Math, though, requires us to be careful, so we want to be as careful as possible. So this should be really similar to the previous problem was. We're just going to product rule again. So this is our first thing and our second thing, or u and v, depending on how you want to think about it. Dy over dx equals, write down the first thing take the derivative of the second thing, which will give us 28x to the 6th plus 0, so we just end that parentheses, plus, write down the second thing, take the derivative of the first thing, so that'll be 15x squared. And at this point, if you don't have a calculator next to you, you're going to be regretting it because there's some big numbers here. I am very lucky that I'm a math teacher and have calculators like just lying around at my house. So 5 times 28 is 140. I add the exponents for the x's and get x to the 9th. Then, like, all we're doing here is distributing, not foiling. So then plus 8 times 28, which is 224, x to the 6th. Distribute here, plus 60 x to the 9th minus 60 x squared. Let's check to see, do we have like terms? These x's can go, x to the 9th can go together as 200 x to the 9th plus 224 x to the 6th minus 60 x squared, which should be our answer. These next two are quotient rule. Now, we talked during the chain rule about how really quotient rules, most of the time we can actually avoid it if we like move things up to the top, and technically that's true even in this case. The problem is that you're likely to mess that up if you try to do it, and I want you to use the quotient rule. So please use the quotient rule when it says to use the quotient rule, and don't worry about that trick. Later on, when it doesn't specify the quotient rule, use that trick of moving things up to the top and giving them a negative exponent, all you want. So for our quotient rule, either we need to think, hey, this is low and high, or u and v, depending on which way you prefer to think about it. So I'm going to do low, d high. So I write down the bottom and take the derivative of the top, which is just going to be 1, minus high, which is x, times the derivative of the bottom, which is just 7, over the square of the one below. We do not need to FOIL the bottom, we just need to get rid of our parentheses and see if there's any like terms to add on top. So this is really just 7x minus 8 minus 7x. So our 7x and our negative 7x are going to cancel, leaving us with negative 8 over 7x minus 8 squared. Which, all things considered, wasn't really that terrible. Number 6 should work out pretty similarly to what we just did. So we've got low and high, or u and v. So I'm going to write down the bottom, times it by the derivative of the top, which is 2x, minus, write down the top, and then write down the derivative of the bottom. Make sure when you do this, the derivative of negative 8x is negative 8. Don't ignore that that negative is there. It's kind of a big deal. The bottom is 3 minus 8x squared. So when I'm working this out, this first thing requires us distributing because we have two things in our parentheses and then one thing. So that's distribution, whatever. Here though, I'm not really distributing, I just have two things to multiply together. So this is going to be 6x minus 16x squared. Negative x squared times negative 8 is a positive 8x squared over 3 minus 8x squared. So I'm going to add my x squareds together and get 6x. That's not supposed to be there. Pretend that didn't happen. 6x minus 8x squared over 3 minus 8x squared. And nothing can cancel here because and nothing could cancel on the previous problem, because the only way to get something to cancel is to try to take out on top what these two things have in common, which is 2x, which leaves us with 3 minus 4x inside of our parentheses. So that's actually really close to being what we have on the bottom, but in math, close isn't usually good enough. And so that means I can't cancel because these things are different. So this really is my best answer for this problem. 7 and 8 don't specify what to use, and we're really just using the power rule again. This time we've got negative exponents, but it doesn't change what we're doing with the power rule. It just means we have to be careful. I'm going to multiply by my exponent and get negative 22. When I subtract 1 from negative 2, I'm going to get negative 3. And so that's important that you remember I'm subtracting 1, so it gets more negative. And then the rest of this is normal. Times by 3 and get 18. Subtract a power and get x squared. This is like multiplying by 1 and then subtracting a power, so I get x to the 0, which gives me just 15. Because x to the 0 goes away whenever we have it, because x to the 0 is just 1. So this is my answer. You don't need to rewrite this with the x cubed on the bottom. If you want to, you can. But it's not necessary because they didn't have it on the bottom when we started. This is very similar without really anything else tricky added to it. It's just basically another problem to practice. So this is 6x plus 8. Negative 3 times 3 is negative 9. Subtract a power and get negative 4. Find the fourth derivative of the function. Now, when we just find dy over dx or take the derivative, we are finding the first derivative. And so finding the fourth derivative means we're going to end up taking the derivative 4 times. So to keep track of that, I'm going to use y prime as my first derivative, if my pen will write. So the first derivative is going to be y prime with just one little apostrophe mark to show it's the first derivative, and then I'm going to basically just do the power rule here. So multiply by my power and then subtract 1. So 12x to the 5th minus 8x to the 3rd plus 10x. That's the first derivative because I've taken the derivative 1 time. Now the second derivative, I'm going to do the derivative of what I got here. So this is going to be 60x to the 4th minus 24x squared plus 10. As I go through this, my coefficients, the numbers in front of my x's, should be getting bigger because I'm going to multiply a bunch, but then my exponent should be getting smaller. So my third derivative, 60 times 4 is 240, x to the 3rd, 24 times 2 is 48, and then just x to the 1st, the plus 10 goes away. My fourth derivative, I usually use just a 4 in parentheses instead of putting 4 apostrophes. 240 times 3 is 720, x squared minus 48. This is my fourth derivative. I will point out that when we were doing this on the homework, they asked us to find the fourth derivative at one point, and like the second derivative ended up being 2. So the third derivative ended up being 0, which means the fourth derivative also ended up being 0. So if something like that were to happen, then if you get 0, everything after that is also 0. Just in case it comes up. It probably won't come up, but I mean, it's better to be safe than sorry. Number 10, we have a function v equals s cubed that describes the volume of a cube v in cubic inches, whose length, width, and height each measure in s inches. Find the instantaneous rate of change of the volume with respect to s when s equals 8 inches. That's a lot of words, and here's what it's asking us to do. Instantaneous rate of change means the derivative. And so I'm going to take the derivative of v equals s cubed. So normally when we take the derivative, if we use a fraction, we put dy over dx, but I don't have a y and an x, so this is going to be dv over ds, because this is the derivative of the volume with respect to s. So the derivative of s cubed is 3s squared. Now it wants me to find that when s is 8 inches, so I'm going to plug in 8. 3 times 8 squared, you do the 8 squared first and get 64, and then times that by 3 and get 192. Our units for this are the units for volume, which is inches cubed, over the units for our side length, which is inches. And if you are having problems with this, go back and look at 3.4 part 1 and look at those notes and the assignment, and you'll see that we found units like this and we took derivatives and all that jazz. So yeah. Number 11 gives us a velocity graph. So in other words, this is saying that at like time 1 second, our velocity is -1 and things like that. It asks us some specific questions. When is the body's acceleration equal to 0? Acceleration is the slope of velocity. So where is the slope of this graph? 0. Well, that happens where it's flat. Here it's 0 and here it's 0. So that means that when we're between 2 and 3, our acceleration is 0, and when we're between 5 and 6, our acceleration is 0, because that's where our slope of velocity is 0. So the way I write that is interval notation, between 2 and 3 and between 5 and 6. When, no, sorry, that doesn't say when, it says what. What is the body's greatest velocity? Well, if this is velocity and I want to know when it's greatest, that's like asking me for a maximum in a way. Now we're used to maximums, finding maximums and minimums like this, but technically a maximum on this graph is where it's highest. So this point right here is the highest place on our graph, or highest isn't really the right word. It's the farthest away from our x-axis. If that had happened down here, it would still be the greatest velocity, even though it was negative. But that's not what happened. So it asks what is the body's greatest velocity. So we're going to answer with 5. If it asked when the greatest velocity was, we would have answered at 10 seconds. But it asked what, so this is going to be 5 feet per second. When does the body reverse direction? Now this requires us understanding our velocity graph. When velocity is negative, our body of whatever this is, our particle, is going left. When our velocity is positive, it's going right. So this point right here represents a reverse in direction, because here beforehand we're going left, here we're going right, so we've reversed directions, we've switched directions. Now over here at 7, it touches the x-axis but doesn't go through, and so it's going right, and then it keeps going right after it basically stops for a moment. So that means that only at 4 are we reversing direction. So at 4 seconds is when it reverses directions. If there was more than one place where it crossed the x-axis, we'd have more than one place where it reversed directions. Also, I can't say anything about t equals 0 because I don't know if before that anything was happening, or if it crossed, or if it didn't. So we just can't speculate about what's happening at t equals 0. There's not enough information. So that is 11. Number 12. Given the distance function s of t, where s is in feet and t is in seconds, find the velocity function and the acceleration function. So this is kind of a big deal. The velocity of something we find by taking the derivative of its position. So the derivative of t squared plus 5t plus 10 is 2t plus 5. The acceleration is the derivative of velocity. So the derivative of 2t plus 5 is simply 2. And that's all it asks us to do there. So cool beans. Now 13 is kind of tricky because we are being asked to find the velocity at t equals 1. They give us the position. So we need to take the derivative of s. And this is a chain rule problem, because I need to change this to be to the 1/2 power, like we pretty much do anytime we see a square root in calculus. We change this to the 1/2 power, and then we take the derivative of this. This has a shell of the 1/2 power and an inside of 5 plus 4t. So we take the derivative of the inside and we times it by the derivative, take the derivative of the outside and times it by the derivative of the inside. So this is going to be v equals 1/2. The inside doesn't change. I subtract a power from 1/2 and get negative 1/2. But then I need to times this by the derivative of 5 plus 4t, which is just 4. Now, if we were simply asked to do the chain rule, then we could be done here, or maybe just do 1/2 times 4 and get 2 and then be done. But the problem is we need to plug in t equals 1 for t, and so it's easier to do that if you will go ahead and simplify. 1/2 times 4 is 2, and move this down to the bottom to give it a positive exponent, as well as change it back to a square root. On the bottom, 5 plus 4t would be to the positive 1/2, because moving it down to the bottom changes the exponent signs. But then we can also say, well, it's the 1/2 power, and so that's really the square root of 5 plus 4t. I want to put a 1 where t is. I'm picking 1 because they told me to pick 1. So work out what this is. 5 plus 4 times 1 is 9. The square root of 9 is 3. So this is 2/3. And our velocity would be in meters per second, which I don't think I put on the solutions to this. And so that's not a super big deal if you didn't put that, but our answer is 2/3 meters per second. Technically, you can plug the 1 in here and type this into your calculator. Your calculator is probably going to say that, oh, that's 0.6 repeating, which we all know is really 2/3, and that's a better answer because it's less rounding. So just a little FYI there about using your calculator. Now, the rest of what we have is going to be using trig function derivatives, and then we're going to see the chain rule. So here, I have to treat these as basically separate problems. X to the 5th is a power rule, so that's 5x to the 4th. Negative cosecant x, I have to have that memorized. The derivative of cosecant x is cosecant x cotangent x with a negative in front. So since it's a negative and our derivative is a negative, this is going to change to plus cosecant x cotangent x. The derivative of 3 is 0, so it goes away, and here's my answer. The next problem, number 15, there are 2 ways of doing it, and one of them is way easier than the other one. You can use the quotient rule here, and it will give you an answer that's like totally fine, but it's not going to look like the answer I would get if I said, hey, I can move this up to the top because of the fact that 1 over sine x is equal to cosecant x. So this is from trigonometry last year. All of the trig functions have a reciprocal function that goes with it. Sine and cosecant go together. Cosine and secant go together. Tangent and cotangent go together. And so if I can remember that, then I can rewrite this as 6 cosecant x. The derivative of 6 cosecant x is negative 6 cosecant x cotangent x, which is like super easy and way easier than the quotient rule. If I do the quotient rule here, then I'm going to have low d high, and this is where people tend to screw up. The derivative of 6 is 0, because 6 is a number. The derivative of a number, the slope of a number, if I graph it, is just 0. Minus high d low. The derivative of sine is cosine. Over the square of the one below. Sine x, if I square it, is sine squared x. And so what I end up with is negative 6 cosine x over sine squared x. Now, it may not look like it, but these two things are the same. They both have a negative 6. Cosine x over sine x is where we get cotangent, and then we still have another sine x left on bottom, which is where we get the cosecant. So if you can brush up on those reciprocal functions, that 1 over sine x is cosecant x, 1 over cosine x is secant x, 1 over tangent is cotangent. If you can remember those, if there's a problem like that on the test, it would be way easier to move it up and do it that way than to use the quotient rule. And the answer looks nicer if you ask me. As a mathematician, this is a better answer than this. But hey, it's whatever. Number 16, find the indicated derivative. 2 apostrophes means we're finding the second derivative. The derivative of 7 sine x is 7 cosine x. Now you may be wondering, why didn't I use the product rule here? 7 is just a number, so I don't have to use the product rule. I only have to use the product rule when this in itself has an x or another trig function, which would mean it would have an x, things like that. And so that's not happening here. So that 7 just gets carried in front. That's very different than when there's a 7 on the inside right here, because that kind of 7 gives us a chain rule that we would have to do. To find the second derivative, I'm going to take the derivative of 7 cosine x. The derivative of cosine is negative sine, so this is going to be negative 7 sine x. And that's my answer. Now let's brush up on the chain rule. Both of these things have a chain rule, just a regular chain rule, not a chain rule where there's an inside and then another inside. So remember that sine to the 5th x is really saying sine x to the 5th power. So the outside of this is the 5th power, the inside is sine x. So if I take the derivative of the 5th power, that's 5 to the 4th, and what's inside is going to be what's inside up here. So 5 sine x to the 4th times the derivative of the inside. The derivative of sine is cosine. Here I have cosine of 10x, and so this time my outside is the cosine and my inside is 10x. Like, look at the difference between those. Here, this is raised to the 5th power. Here, our extra number is inside, and so cosine is the outside here. So I'm going to take the derivative of, and actually there's a negative in front of that I probably should not forget about. The derivative of negative cosine will be positive sine, and whatever I started out with inside has to stay inside. So this is sine 10x. Then I times it by the derivative of the inside. The inside of this is 10x. The derivative of that is 10. The way we would want to rewrite this is 5 sine to the 4th x cosine x. This 4th power, this is not good math grammar to leave it out here. We write that in between sine and x as sine to the 4th. And this cosine x does not get to go inside the parentheses. So the cosine x is not to the 4th power. So it's just regular cosine x. You can put the cosine x in front of the sine to the 4th x if you want to, but you don't have to. Then I'm going to move this 10 and put it in front of sine. And then this is the best answer. Now, the thing with sine and cosine and all these trig functions is what's inside of here is protected. It cannot be messed with except for in like super extreme and really technical like ways. And so we're not going to need to do that because we're in introductory calculus, so we're not going to worry about stuff like that. So I can't put this 10 inside with the 10x and change this to 100x. It doesn't work like that. The 10 can go in front of sine. It cannot go inside of sine, and it will never be able to do that, basically. So don't try and do that. So this is our answer right here. 18. So this 2 is in front of tangent. The 2 is not being cubed, just tangent x is being cubed. So this is a chain rule where 2 cubed is my outside and tangent x is my inside. So this is the power rule. I'm going to multiply 2 and 3 together, which I did not just do. So 2 and 3 gives us 6. And then inside of my parentheses is tangent squared. Because initially I don't change the inside of the parentheses. I have to times it by the derivative of what's inside. The derivative of tangent x is secant squared x. All I can do to this is move this squared inside to right here. So this is 6 tangent squared x secant squared x. I want to use the fact that a square root is a 1/2 power. And then use the chain rule. So my shell is the 1/2 power. And then 14x minus x to the 7th is the inside. So this is going to be 1/2 14x minus x to the 7th. I'm going to subtract a power from 1/2, which gives me negative 1/2. And then I need to times this by the derivative of the inside, which gives me 14 minus 7x to the 6th. You can leave this alone. If I try to do anything, if I want to multiply 1/2 and this parentheses together, I will have to distribute. And so that would give me 7 minus 3.5 x to the 6, or 7 minus 7/2 x to the 6, times 14x minus x to the 7th to the negative 1/2, which isn't necessarily a better answer. So you don't really have to do that unless you want to. But this would still be in parentheses, and both of them have to get multiplied by 1/2. We can also move this down to the bottom if we want and change it back to a square root, but we don't have to if we don't want to. 20 has a square root on the bottom. So the difference is that not only are we going to change it to the 1/2 power, but we want to move it up to the top and make it be a negative 1/2. This 1 on top would go in front of our parentheses. Then we have 5 minus 4x, and we're going to put that to the negative 1/2 power, because on bottom it's positive 1/2. But when I move it to the top, I change the exponent. That is the easiest way to do this. If you don't move it up to the top, you are stuck quotient ruling this, and nobody wants to do that. Like, if you can avoid the quotient rule, then by all means avoid it. If this had been anything other than 1, whatever it is has to go in front of this parentheses. So if it was a different number like 2 or 3 or 4, it would make more of a difference. Since it's 1, we can basically ignore that it's there, because that's what we do with 1s most of the time. If it was something like x, and there was an x in front, then we'd be stuck doing the product rule, which is better than the quotient rule, but we'd still have to do more if this was something that was actually a function like x or sine x or something more complicated. It's not, so hooray, we don't have to do that. We just need to chain rule this. The outside is negative 1/2, is the negative 1/2 power. The inside is 5 minus 4x. The derivative of the outside is negative 1/2 times 5 minus 4x. Don't forget to subtract 1 from this. Negative 1/2 minus 1 is negative 3/2. Then we're going to times this by the derivative of 5 minus 4x, which is just negative 4. So this is the case where I should definitely multiply these together, because that makes this look nicer. That would be a positive 2 times 5 minus 4x to the negative 3/2. And then I'm going to call that good. So there is the review for the middle of chapter 3.